Welcome to the DemoSat showcase video, a practical demonstration of the achievements of the tiny runtime to run model-based software on CubeSat's project. The goal of the project is to demonstrate the applicability of model-based software engineering approach on low-resource platforms such as those used in CubeSats. The used MBSE environment is TASTE, a toolchain developed under the initiative of the European Space Agency. It is dedicated to embedded, real-time systems and supports both model specification and flight code generation. The key technologies involved are AADL, Architecture Analysis and Design Language, ASN1, Abstract Syntax Notation 1 for data modeling, and SDL, Specification and Description Language for behavior modeling. Software designed in TASTE can target multiple embedded platforms, such as ARM and Spark-based systems, and thanks to the presented project, also the MSP430 family of microcontrollers, characterized by ultra-low power usage, the availability of radiation-hardened versions, and low cost. In order to demonstrate a practical application of the TASTE toolchain and the developed MSP430 support, a mock CubeSat class system was designed. The onboard computer is built around MSP430 FR5969 MCU, which is based on a 16-bit RISC architecture, can run at up to 16 MHz, and provides 64 KB of non-volatile ferroelectric random access memory. The system provides CubeSat class features such as mode management, power supply monitoring, thermal management, and simple payload management. Its command and control interface, exposed over a serial link, is ECSS PUSC standard compliant and provides tailored standard services for request verification, device access, and housekeeping, as well as a non-standard service for mode management. The device access service is used to control a mock payload. Here you can see a FlatSat configuration of the DemoSat. The FR5969 Launchpad Evaluation Kit serving as the onboard computer is less than 10 cm in length. The solar panel provides power to the thermal management subsystem. The display emulates a simple payload. The thermal subsystem consists of a PWM-controlled heater and I2² thermometer. The MCU is connected to a PC using micro USB cable, which provides emulated serial communication and power. A rough initial design of the DemoSat was iterated in Capella and then redesigned in detail using the TASTE toolchain, serving both as modeling and code generation tool. The logical architecture is described using AADL through a so-called interface view. Mission control function represents a graphical user interface for controlling the system. Command dispatcher function is responsible for request verification and routing. Mode manager function manages high-level modes of the system such as safe, idle, and operational. Payload manager function manages the payload. Thermal manager function provides the thermal control. Housekeeping function produces housekeeping telemetry. And finally, HAL function abstracts the low-level access to the MSP430 hardware and peripherals. All the functions are connected through multiple synchronous and asynchronous interfaces. Physical architecture is described using AADL through a so-called deployment view. Mission control function is deployed onto a Linux partition hosted by a PC-based EGSE, or Electrical Ground Support Equipment. The rest of the functions is deployed onto an MSP430 partition inside the CubeSat. All connections between the CubeSat and the GSC functions are bound to a serial interface, which is handled by a dedicated device on each node. The data exchange through the interfaces is defined using ASN1 language. The definitions were automatically generated using a PUSC deployment tool to ensure PUSC compliance. The behavior of most system functions is defined in SDL. Each SDL model defines a deterministic state machine which reacts to external signals by executing state transitions, during which it can process data and set its own signals. The complexity of the designed models is representative of real-world applications. Low-level peripheral handling was programmed in C. Additional drivers for TASTE communication devices are coded in C and ADA. The implementation of the graphical user interface, represented by the mission control function, is automatically generated based on the interface specifications. It provides separate panels for monitoring the housekeeping data, sending commands, receiving reports. User can plot the telemetry values of his choice, in this case, the solar panel voltage, and temperatures, the target and the current one. Now, we'll go through a demonstration scenario illustrating nominal operations and an autonomous entrance into the safe mode. The current satellite mode is idle, thermal is enabled, payload is disabled, and the solar panel provides a nominal voltage. Let's update the configuration and set a new safe mode entry threshold voltage. Let's set it to 3 volts. The request to set the threshold voltage is sent and confirmed. Now let's send thermal control parameters, target temperature, as well as proportional and integral coefficients for a PI controller. Let's set the temperature to 45 degrees Celsius. The coefficient values were manually tuned. The request is sent and confirmed. Please note that the target temperature in the housekeeping telemetry changes to the desired value. Heater starts and solar panel voltage drops under the load. For simplicity of the hardware setup, solar panel output is not regulated through a power point tracking algorithm. It is connected directly to the heater PWM, and so its power output is not constant, causing some nonlinear behavior of the PI controller. Let's wait until the temperature stabilizes. The video feed is sped up 16 times for your convenience. The temperature is now stable. Let's switch to the operational mode. The request is sent and confirmed. Please note that the payload is now enabled. Let's turn the payload display on using a standard push-to request with an instruction to distribute an on-off device command. The request is sent and confirmed. Please note that the display is now turned on and a yellow bar is visible. Let's send some data to the display using a standard push-to request with an instruction to distribute a register load command. The data to be sent is 42, one of the primary pseudo-perfect numbers. The request is sent and confirmed. 42 is now visible on the display. Let's send some more data, this time a 137, an Eisenstein prime. The request is sent and confirmed. 137 is now visible on the display. Let's simulate a power loss by reducing the light source intensity. Please note the drop in the solar panel voltage and the consequent temperature drop. When the voltage reaches the configured threshold, the satellite automatically switches to the safe mode, disabling the payload and heating, reducing the load on the solar panel and allowing the voltage to recover to the level allowed by the incoming luminosity. With the thermal control disabled, the system is slowly cooling down. Let's return the light source intensity to the nominal level. Please note that the solar panel voltage increases. Satellite can be now safely switched back to the idle mode. The request is sent and confirmed. Thermal control is re-enabled and the temperature slowly returns to the desired value. The load from the heater is again visible on the solar panel voltage plot. This concludes the demonstration. If you want to know more about Taste or N7 Space and its products, please visit the following sites: taste.tools and n7space.com. Thank you for your attention.